Okay, I'm so excited to talk to you today about thermodynamics. Thermodynamics is the study of changing energy within a chemical system. And I'm excited to talk about it in the context of chemistry because energy is the driving force behind why chemical reactions occur. So a lot of the times in chemistry classes, we just teach you, well, this is sort of the way that things are, but this really gets at some of the underpinnings of why things happen. They are energetically favorable. And so in order to talk about energy in a chemical context, we have to start by defining some terms and talking in a more conceptual way about heat and work and energy within chemical contexts. So let's define some terms. We talked a little bit about energy in past videos. We said that energy is the capacity to do work, and work in a scientific context, which is abbreviated with a small w here, is the energy transfer, or we talk about the energy flow into or out of a system. So we are moving energy around from one place to another, and that's causing things to happen. We are doing work or overcoming some sort of resistance is another way of thinking about work. So we talk about into or out of a system. Now, a system is something that we as the scientist in our experiment are going to define. A system is a substance or a mixture that is singled out that we have chosen to study, and we're going to focus then on that system and everything around it. So the surroundings then are defined as everything that's in close proximity to that system, and that system might have an impact on those surroundings, or the surroundings might have an impact on the system, and the flow of energy from one to the other is work. Essentially, that's kind of conceptually what we're talking about here. So let's say that we have a piston here set up. It's a great little drawing. Let's say that we have some fuel in here. So let's say that we're going to do some sort of combustion reaction. So we have a hydrocarbon, we have some oxygen in there. We're going to do some burning of fuels. That's going to create some gases. These gases are going to be created in this space. These gases are also going to be moving around a lot more. These particles in motion are going to be a lot more warm. It's going to increase the temperature. It's going to cause some energy to move from our system here. This is my chemical system, to my surroundings, which is my piston here. And then that flow is going to cause my piston to move upwards, right? So I have energy from my system. It's releasing this amount of heat. It's releasing this amount of energy. This energy is flowing from the system into the surroundings and causing chemical work, right? So I'm doing some sort of chemistry here, to mechanical work. So I'm physically moving some sort of piece, some sort of mechanism here in my surroundings from the energy from this particular system. Now, we can do this because of the law of conservation of energy. Law of conservation of energy says that I can convert or transfer energy from one form to another, but I can also transfer it from one thing to another, right? I can if I'm thinking about flipping a coin or throwing a ball, then the kinetic energy from my hand is going to be transferred to that ball. So my hand would be the system, the ball would be the surroundings, and then that transfer of energy, that flow of energy, is the work that's happening. So by definition, if we have work that's flowing from the system into the surroundings, so like in this case, with my piston, we call that negative work. So we define that as being negative work because our system is losing energy, essentially. The energy is moving out of the system. So that's a bad thing for the system, right? We want a lot of energy there. But when we lose the energy, then we define this as negative work. If the surroundings, on the other hand, there was some sort of energy there and it was being absorbed by the system, we define that as positive work. So we can have energy, and energy has some sort of, units that are associated with it, or SI units for energy, or joules, or we could think about it in terms of kilojoules. If that's a positive value, it means that the system is absorbing that energy. So we're taking that in. That would be, in this setup here, as if I was pushing down on this piston, right? If I push down on this piston, that would compress these gases. An increase in pressure would mean an increase in temperature. So I would be transferring all this energy, or even the kinetic energy of this thing moving, to the energy of my system. So from the surroundings into the system. That's positive work, more energy coming in, transferring in. So we define that as a positive quantity. From the system into surroundings, we're losing it, we're evolving heat, then that's going to be a negative work. Now this feels a little bit backwards, and it's important to keep in mind because there's no such thing as negative energy, right? I can't have a negative number of joules because remember, a joule is a kilogram meter squared per second squared. So I can't have a negative quantity that includes mass and length and time because we can't have negative quantities for any of those. So this is just by convention. This tells you information about your system and your surroundings. It's not that I actually have negative energy because there's just no such thing. All right, now this energy flow from the system into the surroundings, or absorbed from the surroundings into the system, is usually perceived as heat. And so as scientists, we define heat, which is abbreviated with Q, usually a lowercase q, as the energy of moving particles. So we could kind of think about that as if I have all the particles in a substance that are moving around, kind of the average energy of those is the heat of that substance. And heat flows along a temperature gradient. And what I mean by that is that it moves from the warm thing to the cold thing. You've probably experienced this if you've gone to a football game outdoors in the fall, right? So you go and they have those metal bleachers, and you go and you sit on those metal bleachers, and all of the heat from your butt immediately moves into the cold bleachers, right? That's that heat flow along a temperature gradient. We can think about it in terms of coffee as well, because I definitely haven't had enough today. So if I have a latte here at, let's use Fahrenheit units, because we in the US are a little more comfortable thinking in those terms. So if I have hot coffee at 180 degrees Fahrenheit, and it's a nice crisp fall day outside, 45 degrees Fahrenheit, then when I'm thinking about my hot coffee and I bring it outside, then I know that my coffee is going to cool off. Well, what does that mean? Well, it means that the particles in my coffee, the heat that's caused by these particles moving around, is going to be transferred from my system, right? If I'm defining my coffee cup here as my system and the outside as my surroundings, then the heat is going to flow from the warm thing to the cooler thing, right? And if we're thinking about this on kind of a particle level, so let's take the wall of my cup. Here's my little coffee particles that are hanging out and moving around. We'll show some motion lines here. They're all hanging out. They're nice and warm, so it's a little dance party in my coffee cup. Okay, now outside, these particles are moving a little bit slower. We're sort of still moving, right? And they're gas particles. They're just kind of hanging out, sort of sluggish. It's chilly, it's fall. But these guys then, you know, there's an insulating layer with your, whatever your cup material is. But these guys are going to be bumping against the cup layer. The outermost ones then are going to get a little more energy, right? We're going to transfer some energy to these guys out here. These guys then are going to bump into these guys, which are going to bump into these guys, which are going to bump into these guys. And the heat is going to move then. It's going to flow, all this energy transfer from one area to the other, from the system into the surroundings. And in the same way that we do with work, we define that heat loss as a negative Q, right? So that's a negative heat from the system into the surroundings is a negative heat amount. Whereas if I had a really hot day and a cold beverage, so now I have lemonade on a summer day, right? Then my lemonade is going to warm up, right? And my ice in there will melt. And the reason is because it's absorbing heat. That would be a positive Q value. Okay, now as chemists, we're of course interested in chemical systems, and we think about this in terms of, you know, what's happening in a lab. If I'm going into an experiment, then what energy can I get out of this process, and why is that important? So in a chemical process, the heat of the reaction is called the enthalpy, and enthalpy is abbreviated with a capital H. Now reactions that evolve heat, so again, we're thinking from the system into surroundings, so we're thinking a negative value, are called exothermic reactions. And therm here refers to heat. So when you think of thermal, like a thermal blanket or thermal underwear, those kinds of things are helping to keep the heat in, right? So that word root there comes from heat. exo, think of this as like exiting out. This is also called exergonic. That's another way that you'll see this written, exergonic or exothermic. I like exothermic because I like the therm part, I like the heat part. Now reactions that absorb heat, meaning that they're cooling down the surrounding temperatures, are going to be defined as positive. And again, this movement of energy, we're not talking about the energy itself being negative because there's no such physical thing, but we're talking about the movement or the change in that energy. And that change, when it's positive, means that it's endothermic. And again, thermic referring to heat. Endo, I think of kind of coming into. So it's coming into the system. I have to put energy in order for the reaction to occur, or in order for something to happen, or the flow of the energy is coming from the surroundings, being absorbed by the system. Those all sort of mean the same things. Now I'm talking a lot in terms of change, and again, these signs are sort of tricky for students traditionally to get their head around, and this is all referring to thermodynamics, or thermochemistry. Dynamics. That's what I get for trying to write and talk at the same time. So thermo, of course, referring to heat. Dynamic refers to change. So when we're talking about thermodynamics in terms of a field of study, we're looking at the changing energy from a system into surroundings or over time or any of those kinds of things. So when we're thinking about change, that's our delta. So we usually talk in terms of kind of our Greek delta, which is that sort of triangle looking symbol that indicates change. So we're looking at a difference in states. So thermodynamics just in general is the study of changing energy. And a lot of this feels like physics, and it is. I mean, one of the greatest chemists, Ernest Rutherford, who's the one who discovered the nucleus of the atom and the proton, he also discovered a lot of cool nuclear stuff. He was definitely a physicist, and he always said that everything is physics and the rest is just stamp collecting. And I kind of generally buy into that, right? I'm a chemist, but so much of the underpinnings of the chemistry come from the physics, come from the energy, come from the moving particles and kind of the different forces that govern that. So this really kind of dives into these ideas. It gives you a little bit of an understanding of some of these concepts. And as always, if you have any questions, feel free to reach out. Otherwise, I'll talk to you again soon.